Okay. Ready to go? Beg your pardon? No worries. Okay. Thank you for everyone coming tonight. On those tonight, we're going to have the team from Swinburne talking about their Formula SAE car for this year. The design's coming along, it's nearly complete on those, and then they're going to start working on putting together their car for this year. But I'd like to start off first with some news, a bit of EV news about what's been happening on those. So there's a lot been happening in the EV world and that in the past month. And of course, the first one everyone's talking about, the Tesla Model 3 was announced on those, and I think just about everyone would know that. But it was amazing what happened with the launch of the Tesla Model 3. They've now come to 400,000 reservations on those, so that's worldwide. People who put down $1,000 deposit on those to reserve one of the cars. And one of the interesting things about that is at the current production of Tesla, that would take them 6 years to produce all of those cars. So it'd be interesting to see what will happen. They'll have to ramp up production, or things will have to change. But some of the features of the Model 3, when it was released, people looked at it and they liked it. It was very much like a small Model S. Same styling, similar styling of car. Some people didn't like the front bumper on those, thought it looked a bit bland from the front. It looks very much, like a Model S, same sort of styling and that in it. The acceleration figures are pretty good. These were just some of the figures that we've released because there really wasn't a lot of detail about the car on those released. But 0 to 100 k's in 6 seconds, a couple of seconds faster than the Leaf. There'll be a dual motor version as well. So Elon Musk announced that they'll make a dual motor version. And the range they were looking at was 212 miles, I think they said, on those in American stuff, so 345 kilometres. And of course, these figures are minimum figures. So hopefully they're saying that they may be able to do better than that when the car is released. So that was the Tesla Model 3. And then there's been a lot of battery research going on, and endless amount of battery research, and this is just some of the things that's come out of that research. Those Samsung's announced this, as well as a Spanish company on those, that they're going to start building batteries with this construction. They've worked out that there's a different way that they can make the anode. The cathode of the battery is, you've got like PO4, which lithium phosphate, and then you had the NMC cathode, which was an improvement, went into power tools. And that's some of the things they've been working on, the cathode of the battery. Now they're working at how they can improve the anode of the battery. So the current batteries use a graphite anode. On those, just a strip of graphite there to absorb the lithium ions on those that come out of the electrolyte when the battery is charged. But the new anode that they're using uses graphene layers with silicon interlaced. The advantage of that is silicon is able to absorb more lithium ions than graphite or graphene is. Actually 6 times the amount of lithium ions, and that can be absorbed by silicon by the shells. So, but the problem with silicon was when you put silicon in an anode, it swells on charging. So they've been trying to get silicon incorporated into the anode, and they found that the way that they've been doing is to coat it with layers of graphene to intersperse the silicon atoms with graphene, which stabilizes the anode and stops it from cracking, so that you can get a reasonable life and that out of the anode from charging. So that's been successful on those. As I said, Samsung's announced it, and so has a Spanish company that's looking at building batteries as well. So there's a few companies doing it. And we're looking at 2 to 3 times the capacity of a lithium-ion cell at the moment. So going up from 200 watt hours per kilogram up to 500, 600, 700 watt hours per kilogram. We're not sure of the figures yet, but that'll make a huge difference in that, and that's using current lithium-ion technology. Another battery that was released last year is the sodium-ion battery on those. So you can see the sodium-ion battery, well, Aqueous Energy has released one that's for home solar systems. It's a heavier battery in this design than what you would put in a car, but since it's sodium-ion, it can use a saltwater electrolyte. It's a very safe battery, as you can see. The electrolyte, salt water, will put out any fires that would come from the battery. It's capable of 100% discharge without any damage. So it can be run flat with no problems. They're looking, Aqueous Energies quote this particular design of battery at 3,000 discharge cycles on those 70% capacity. So that's pretty good. It's as good as the best of the lithium iron phosphates and that are available now. And simplified battery management because the battery is self-balancing. So it doesn't necessarily require individual cell monitoring on those on the battery. So that simplifies the electronics as well as making it more reliable. But the same battery has also been released, is being developed actually. They haven't released this battery yet by Faraday, and they're looking at a pouch cell, so something that would suit vehicles. The little pouch cells are looking at the 3 ampere hour ones there. They put them in an e-bike, a test in an e-bike, but they've been confident they get similar results to lithium iron phosphate and with these pouch cells on those in an e-bike. But one of the advantages we can see there is that the amount of sodium that we have on the Earth, when you compare sodium there, 2.6% of the actual Earth's crust, the mineral formation of the Earth, whereas lithium, 0.005%. You know, if we have all these Model 3s made and Tesla was to do that and make 400,000 cars on those, we're looking at the limit of the lithium that's currently available on those that can be mined at the moment. So that's going to be a problem moving forward with a mass adoption of electric cars, is how much lithium in that is available. So sodium would be another choice, another possibility. These particular pouch cells can be made on the existing lithium-ion battery manufacturing, you know, production lines, I suppose you'd call it, yes. So they use the same construction method. So that was some of the news that's come up so far. In battery development, there's been some amazing things happening. Okay, well, I'd like to hand it over to the people from Swinburne, from the lads from Swinburne now, to talk about their car. Shall I close that down? Okay.
Hi, I'm Denham. I'm the P&E section leader for Team Swim of 2016. This is Matthew Priestley, and he's one of the core P&E members. So Team Swimburne is a student-run project through Swimburne University where we design, build and race an electric race car. We're currently wrapping up our design phase at the moment, and then during the semester break, we will start assembling it. Then we're hoping to go for 3 months of testing, and then at the end of the year, we will compete against the other universities in the SAE Australasian competition. So our team goals, we'd like to come first overall this year. The way we'd like to achieve this is by coming top 5 in every event. The 3 months of testing to get the most out of our car, to validate our designs and do tweaking and tuning to make sure it can be the best car that it can be, and an overall weight of 240 kilograms. So The SAE competition, it's split into two parts with the static events and the dynamic events. There's the scrutineering with the electrical and mechanical side. Design, where we have judges come and inspect their car from different areas. And then there's a cost report and a business side where we have to try and sell the car. And once we've passed all these, we go on to the dynamic events where we have an acceleration and a brake test, skid pan, which is like a figure 8 to test the cornering of the car, autocross, 1 hot lap, and then the 22-kilometer endurance. So as a design iterations over the years, here's our 13 and 14 cars. This is 2015, our last year's car. And this is our 2016 car as it stands at the moment. So the vehicle architecture we're going with this year, we're going to run 2 Tritium Wave Sculptor 200 motor controllers, and they'll be powering 2 MRAX 228 motors with a spur reduction gearbox to try and get them into the most efficient zone. And these will all be packaged in a carbon fiber monocoque chassis. So I'll pass on, Matthew, talk about our P&E goals.
So our P&E goals this year was, first of all, we've got to meet 42 kilos for our section to get within the 240 kilos allowed for the entire car. Our second goal was 0 electrical performance interruptions during practical endurances. This is so that when we're actually running the 22-kilometer endurance run, nothing in the P&E section breaks down and stops the car, so we can actually finish. The third one's a full systems operational check, debug, pre-charge within 30 minutes prior to testing. This allows us to basically rock up at the events, turn the keys, and go. If you can't charge within 30 minutes, we're in big trouble.
So as an overall system breakdown of the power electronic modules in the car, we have a throttle module at the front, a dash and data logger near the steering housing, Quanta Boards on each corner of the car, an LV safety system, and then the HV system. So this is how the car stands electrically. So throttle module in the front, connecting to the sensors, dash visible to the driver, the HV system and the LV system hidden behind the firewall, and then the 2 motor controllers on either side, and then we have fans and pumps to cooling on the sides of the car. So start off with the throttle module at the front, connects to potentiometers and brake pressure transducers near the pedals. It communicates to the dash and the LV power board and over CAN bus, and also sends drive commands over CAN bus to the motor controllers, and also has a green safety loop built into it. So the concept of it was to read sensor values and to send drive commands to the motor controllers as a percentage of how much we want to spin the wheels, and has analog safety requirements to follow the SAE rules, which include a 10% difference in pedal readings if they're out of range of where they're supposed to be. And this is also with the brake pressure. So it's pretty much to double check nothing has gone wrong and that the car is still safe to drive. So sensors we're using on the accelerometer pedal, we're using throttle position sensors as a rotary pot. There is a linear potentiometer on the steering rack, and there's also brake pressure transducers for the brake lines. So for the dash and data logger, the idea is we have status lights, so we have to indicate to the driver. So this is to tell if the AMS or the IMD has had a fault and what is the state of the safety loops. As a data logger, we want to try and log as much telemetry as we can this year. So this will be from the Quanta Boards, which have accelerometers and gyros on them. Information from motor controllers, so this will have temperatures, speeds, and yep. And this is all over CAN bus, and we're hoping to log this onto an SD card that can be easily removed. Then we can just chuck it onto a laptop, see what information we have, put it back into the car and keep going. So Quanta Boards, we're looking into hopefully doing torque vectoring. So these have a accelerometer and gyroscope in a tiny little package that sit on the corner near each wheel of the car. So this will all be logged, and it's to help validate designs that people have had, and we can also do future research using this data. So LV power board, the main concept of it is to monitor the safety loops throughout the car. So we have e-stops, circuitry on the throttle module, and a tractive loop to make sure HV is okay. And it also has an AUX power supply for the LV components on the car. So as a diagram to show you how it works, so we have the batteries. We use graphene LiPo batteries. These are monitored by BMS. These are turned on when we turn on the first LV key. And then the micro now gets power, so it can check the condition of the e-stops. And then we can turn the HV key if all the e-stops are closed. And then it would check all the safety loops to go. Then we are ready to pre-charge our HV system. So we have 3 safety loops. We have a green loop and a blue loop. The blue loop is mainly the emergency stops on the outside of the car, and also with the brake over travel switch. And again, using graphene batteries, and this is all tidied away in a nice enclosure behind the firewall. So with the HV side, we have an AMS that monitors the BMSs on the accumulator. And this also supplies power to the motor controllers, which is then turned into 3-phase for the MRAX motors. We also have a 5 kilowatt braking rule, and this will communicate to the throttle module as well to tell it to brake the green loop and to stop the car if the driver has braked in an emergency. So this is what our accumulator looks like. We're using 18650 cells this year for the robustness, and they've got really good energy capacity. And yeah, so we'll now pass on Matthew to talk about how we're going to connect everything together this year.
So basically, my job this year was to sort out the looming of the entire car. Last year's loom was fairly good. We're just improving upon last year's design by reducing the length of the loom. In turn, we can reduce our costs and reduce our failure points within the loom itself. It's fairly important now. The main sort of goal was to try and cut some weight out. So last year's loom was 117 meters in length, which weighed about 1.5 kilos. This year, we've got it at 79 meters, about 800 grams or so. So we've taken almost 30% out of the loom, which is a great effort, just by routing things more efficiently and using less connectors, which is great. For the connections this year, we used some Sauer Autosport connectors, which you might have saw a couple slides ago. We replaced them with these new Deutsch Amp Seal black connections. The advantage with these is they're PCB mounted, they're waterproof. So for modules that aren't behind the firewall, if any water or brake fluid or any sort of fluids get behind there, the boards will stay safe. And to mount the entire loom to the chassis, we're using P-clips, just because they're a really simple idea and they work. So for our 3-month testing, we plan to develop our system to be fail-safe to last the endurance. That's so we can score maximum points and win the competition. We also need to troubleshoot our systems in 3 months, so our system is as robust as possible. So things don't have to be replaced.
Thank you for listening. Are there any questions? No. Yep. Oh, there is a bit of differential action. Yep. So they are separated. Yep. They're physically separated. So they each have their own gearbox and housing, and they connect each wheel independently.
What's the weight of the current model that you're looking at, and how does it compare with last year's car?
We're aiming for 240 kilos, and that's on par with last year's car. Yep.
So some of the items are heavier, as well as weight that you're saving.
So the idea is by making some of our enclosures smaller and more efficient with their materials and decreasing things like looming, we can actually add material into places which need it. So something like the accumulator, which houses the battery, is a potentially volatile piece of equipment. So we want to save weight in some places so we can make sure that our accumulator is 100% fail-safe, really. So it's just redistributing things. And then it also allows us to weight distribute the car better as well by having things smaller, so we can put heavier items in certain places to balance the car out and make it easier to drive. Kyle?
Actual time in designing a composite structure quite time consuming. So the aluminium structure, although at the moment it causes you gain 7 kilograms, and that is supposed to have elsewhere on the car, which means you have the accumulator aspect of the testing. There are also other weight elsewhere added to the car. In the latest revision, we do have a basic aero kit and various other different things incorporated into the suspension that have increased the weight by approximately 10 kilograms. So breaking even, as fast as we've done mostly by varying the battery chemistry, so we actually dropped 7 kilos by varying the chemistry, as well as taking a lot of weight out of the chassis and the steel parts and stuff.
So the capacity and voltage, looking at a total overall 420 volts DC. So we have stacks that the little 18650 cells come in. So it comes in about a stack of 8, and then we have 100 of these in series. Amp hours, 20. Yep. Yeah, because these are much more robust and won't explode if we drop them this time. Yeah.
You have a 1C discharge, I've heard before. Is that correct?
1C discharge. No. Yeah. No, it's something we have designed in-house. Yeah, it's like something we would like to do, but it's like our main prioritization at the moment is getting the car into the track. Yeah. Yeah. Yeah, and we have quite a few people each year doing final year projects, trying to validate the designs of going towards torque vectoring.
I'm not sure if I missed this, but how many accumulators are you actually making just like once, or is it spares out?
Only one accumulator, but with these cells, it's much more serviceable. So we can actually have spare stacks. So if a cell does die, it's much easier to take out one of the modules, replace the stack, and put it back in. I would say we're rolling over about half of last year's design. So there were a lot of things we like, but it's more refining this year. And so because we did get out onto the track and we did discover some things we really do like and a couple other things that do need to be fixed. But we also have a design consideration of backwards compatibility with last year's. So if a part, say, is not ready in time, or if it does unfortunately break, we can put on a part from a previous year.
Quanta Boards.
Yep.
Is that really
Yep. So they have a accelerometer and gyroscope on each corner of the car, and we just like that data to see how the car's performing the way we expect it to be.
Gains in aero, or is there you're not concerned with the aero?
Yeah, the aero people are working on a wing package, so yeah, would like more downforce.
Yeah, just to elaborate on that, the way they figured out the aero to work this year is they want as little aero as possible in terms of drag, just because they figured out for 4 out of the 5 events you need low downforce, so you can have your motors powered up more to actually get around the track. So they're working on designs that generate high downforce with low drag. So I think the latest one had 30 newtons or so on the front wing, with only a little bit of drag on it, and then they're doing current iterations on the side pods and rear wing to make the package work as one, really.
So yeah, the right-hand wheel would spin a little bit faster, and then we can also decrease the power a bit on the left-hand wheel as well to get that full corner torque. We do have an overall max power we're allowed to use. It's just like we would have it as a percentage through a control loop.
Thank you, guys. Any more questions? No? Thank you. Thank you for that. Okay, well, we can just go for, I think the coffee room or tea room we use is upstairs. What, 5th or 6th? The 6th floor, is it? I know, so we might go up into the 6th floor, things on that. I was just thinking too, like in some of the work that I've been doing as well, with the Vectrix scooters, on those, I've worked out a system whereby you can charge the Vectrix scooter in half an hour off a J1772, off the public charging stations, without having to use a fast charger. So yeah, there's some more work that we've been doing on the Vectrix and that as well. So that's been interesting, and that to be happening. Well, anyway, let's go and have a cup of tea and a chat. Okay.